Hello guys. So today we're going to discuss understanding the bias variance trade-off. This is a very common machine learning interview question. So, okay, let's just dive directly into it. What is a bias? Bias is the difference between average prediction of our model and the correct value which we're trying to predict. And both of like we're talking about supervised learning right now. So we have labels of the data points as well, right? So bias is the difference between, so we have an average prediction of all the data points, and then we're going to calculate the ground truth. So the distance between that is the bias, right? So model with high bias, what does a model with high bias means? High bias means that the difference between the average prediction of our model and the correct value, the ground truth, is going to be large, right? So with high bias pays very little attention to the training data. Okay. So high bias pays very little attention to the training data and oversimplifies the model. It always leads to higher error on training and test data. So high bias pays very little attention to the training data and oversimplifies the model. Basically, you're not really caring what the training data looks like. Your distance between the predicted your average prediction of our model and the correct value is large. You're not really giving much attention to the training data, and it oversimplifies the model. It always leads to high errors on test and training data. What is variance though? So variance is a variable. So every time you come across a data point, the effect that it's going to have over the model training is going to represent what variance is, like what variance is. Variance is the variability of model prediction for a given data point or a value which tells a spread of our data. Model with high variance pays a lot of attention to the training data. So this is the opposite of a model with high bias. High bias does not, high bias means that you're not really caring about the training data. High variance, in fact, means that there is a lot of spread of the data and you are caring very much. You're basically trying to train your model exactly or close enough to your data points, to each of the data points that you encounter. And so this does not generalize on the data which it hasn't seen before. As a result, such models perform very well on training data but have high error rates on the test data. So mathematically, we're going to delve into this. What is this? So as we discussed, what is bias? Bias is that there's an average prediction, and average prediction minus this f of x. So this is the average prediction of all the data points, and this f of x basically represents the ground truth value. So distance between the two, difference between the two, this is the difference, and we have squared it to basically make it more mathematically amenable. We do not want to deal with negative values. It's a similar, that's usually why we want to square things anyway in maths, especially when we're building models. But yeah, so here what we've done is we've calculated the expectation of, so as we said, variance is the variance, like for every data point that we encounter, we're trying to calculate the distance of that data point from the average. We're basically trying to see that every time we introduce a data point, what is going to be the variability, what is going to be the effect it has on the model training. Basically, that's what we're trying to capture in this equation, right? So this is calculating distance between the data point and your average, and then you're squaring that. You're calculating the variance, the spread of your data, right? And there's something called irreducible error. Irreducible error is the error that can't be reduced by creating good models. It is a measure of the amount of noise in our data. Here it is important to understand that no matter how good we make our model, our data will have certain amount of noise or irreducible error that cannot be removed, right? Okay. So bias and variance using bullseye diagram. Okay, so these four diagrams are very useful if you want to remember the concepts. High bias, low variance, underfitting. This figure and this figure you should try to remember. Okay, so high bias, as we discussed, this is the ground truth, this is the average, and there is a huge difference between them. So this is causing underfitting. You're not really caring about the you're not really caring about the distribution of the data itself. You just, you know, like if this is the real distribution, you're not really caring about the distribution of the data itself, right? Okay, so there is a high variance. High variance means there is a lot of spread of data. High bias and high variance, you're still away from the ground truth of the data, and there's a lot of spread of the data. Okay, this is not as bad a case as this one, where we have basically not we have stopped caring about the training data itself. We've just simplified that, all our we have just learned a very simplified model, which is not truly capturing. So this is our ground truth. This is our truth, and this is and now a bit of discussing low bias and low variance. And this is preferred basically. So low bias means that your average of the data points is not far away from your truth, and basically your what that means is that if you encounter a new data point, it generalizes well, so it's not going to be far away from your from the model that you have learned, right? So that's low bias. And low variance again means that model data is not spread so far apart that you have to learn a very complex model. Basically you want to obviously minimize the error, right? You want to minimize the distance between your model, your basically boundary. For instance, if we're discussing a classification problem, a two-way classification problem, basically you want to minimize the distance, so you do want low variance as well. So this is your ideal case, right? Low bias and low variance. And then there is low bias and high variance. Now this is overfitting, underfitting, and overfitting. Overfitting is the opposite of underfitting. So basically, there is a low bias. Your data points are, not as far away. Here you could see the truth is there, the data points are there. Here, that's not the case. The data points are not that far, but basically you have learned very closely to your data points. Like your model is very close to the model that you've learned, the boundary that you have learned is very what do you say, very variable, um, with respect to your data points, right? So in supervised learning, underfitting happens when a model is unable to capture the underlying pattern of the data. Underfitting happens when a model is unable to capture the underlying pattern of the data. So these are the oversimplified models. These models usually have high bias and low variance. So high bias again, what did high bias mean? High bias meant that your ground truth is far away from the basically the average of your data points. Sorry. And it happens when we have very less amount of data to build an accurate model, or when we try to build a linear model with the nonlinear data. So if we oversimplify the model that we have learned, then these models are very simple to capture, very simple to capture the complex patterns in data, like linear and logistic regression. In supervised learning, overfitting happens. So underfitting happens and overfitting also happens. Overfitting happens when our model captures the noise along with the underlying pattern in the data. And I think it's not just the noise. It's like, there is always so for instance, think about it. You have data set of your dogs. They're going to be all sorts of different dogs, right? So there is always going to be a variance, like in your data. So it's not just a noise, right? So if you learn too closely to those data points, then you will not have a very good model, right? It happens when we train our model a lot. Basically you want to understand the concept of a dog rather than its color values, or its size, right? It happens when we train a model a lot over noisy data set. These models have low bias and high variance. These models are very complex, like decision trees, which are prone to overfitting. So decision trees are prone to overfitting. Okay. Okay. We're going to discuss decision trees at some point as well. So this is overfitting, as we discussed. All the data you're trying to capture all the variability in your data set. The problem is that that's like if you encounter a new data point that is not going to generalize very well, right? So, and this is underfitting. Underfitting is that you have all this variation, but you're completely ignoring this variation and you are, learning a very simple model. Now, then there is a good balance. Low bias and low variance, as we discussed, that is the perfect blend for us. So there is a low variance. So there is as we can see here, this is going to be like n raised to power 20 dimensions, right? And this is n square, right? So we are capturing the variance between data as well, but following we're not following every data point. We're not over capturing it, right? So there is a low bias as well, because all these data points, as you can see, like this is our boundaries, this is our average, so they're not far away from it, right? So low bias, low variance, good balance. Why is bias variance trade-off? If a model is too simple and has very few parameters, then it may have high bias and low variance. On the other hand, if a model has large number of parameters and um, we discussed high bias and low variance simplistic, very few parameters, our model has, and if a model has large number of parameters, then it's going to have high variance and low bias. So we need to find the right or good balance without overfitting and underfitting the data. This trade-off is in complexity is why there is a trade-off between bias and variance. An algorithm can't be more complex and less complex at the same time. To build a good model, we need to find a good balance between bias and variance such that it minimizes the total error. Find a good balance between bias and variance such that it minimizes the total error. So we said that this is a total error, right? Bias square plus variance plus irreducible error. So basically, what this graph shows is this is algorithm complexity. This is the error. So algorithm complexity is, you basically think of it as the dimension of the boundary that you've learned. For instance, as I mentioned, this could be n raised to power 20, then this is n square, and this is just a straight line, right? So this total error is basically this error, variance plus bias square plus irreducible error. And so this is how the red line is captured. It's the combination of this plus irreducible error, right? And as we can see, the irreducible error is more of a constant, right? So what did we want? What do we want? We want something here, like this is our ideal point, right? So here the variance is low and the bias is also low enough, and this is our ideal point. An optimal balance of bias and variance would never overfit and underfit the model. Therefore, understanding bias and variance is critical for understanding the behavior of prediction models. Okay, guys. I hope you understand it well. If you do not understand something, please feel free to just, comment on the video and I'll get back to you. Thank you.